This is our video review key for chapters 26 through 27. So first you will notice on our memory aids that when you look at it, we don't have a lot of formulas. So instead of a formula for each different hypothesis test, we only have this one basic test, or one basic test statistic. Our test statistic for every test is just z equals our observed minus our expected value over our standard error, and that works for every test. And then we just have hints to help you remember what your different expected values and standard errors would be. So you have one for percentages, you have one for averages, you have SD plus and the degrees of freedom. Remember, this is for your t-test. That's the only time that you have to use those is for your t-test. And you have SE difference, which is what you use if you have a two-sample test. Either of the two-sample tests will use this. So again, one test statistic, but slightly different expected value and standard errors based on what you're working with. Now, for every problem, no matter what the problem tells you, you have to follow these steps on the review. So these steps being, you need to go through and say, well, which test should you use? And along with that, you should also know, is it one-tailed or two-tailed? And then you also need to be able to tell me, is it a one sample or is it two sample? Now those two things don't affect each other. You can have one tail, two samples, one tail, one sample. Sorry, these two things don't affect each other. You should be able to tell me how many tails you did and how many samples. You need to be able to tell me the null and alternative hypotheses. You need to find a test statistic, find the p-value, interpret the p-value. You need to know whether or not you should reject or fail to reject the null hypothesis. And if it doesn't tell us the significance level, we'll just always use that 5%. And you have to state your conclusions in the real world context. And that will always be where you say found evidence or did not find evidence. So what I want you to do on every test, no matter what questions I ask you about each situation, I want you to do all of these steps. Because on the exam, what I see people mess up on time after time again is they don't do this. Make sure you write out every single step yourself first, then look at what questions she's asking you, then kind of pick the right answers to match hers. But do all of this yourself first. So you'll notice the reviews look kind of funny. And it's because I'm trying to encourage you to do that. In this example, the Center for Disease Control, the CDC, sends 4 identical samples of bubonic plague cultures to the ACME Biological Analysis Lab and asks the lab to measure the level of antigen in each sample. The lab is not told that the samples are identical and should have an average antigen level of 40. The lab reports antigen levels of 41, 47, 36, and 50. The average of these 44 measurements is 43.5 and the SD is 5.41. So we want to test to see that the measurements on average are equal to 40, which is what they were supposed to be if the lab is working correctly. Or are the lab measurements biased? Are they too high? So let's write down things that were given. To me, that always helps me figure out what I'm supposed to do for a problem. So I'm going to write down, I have a sample size equals 4. We had a sample average equals 43.5 and my SD equals 5.41. So that's what I was given. We want to see, is the average too high? Or basically, is the average, we'll say, higher than, it was supposed to be 40. So we want to know, is the average higher than 40? So when I read this, it makes me think I'm doing a hypothesis test. I need to figure out which hypothesis test. I only have one sample. Now, is it going to be a z-test or a t-test? I know I want it for averages, but I need to decide between z and t. I'm going to say T is a one sample z-test for averages because my sample size is less than 30. So anytime we have that sample size less than 30, we'll use a t-test for our averages. Okay, so for our test part, we should write our hypotheses. The null hypothesis would be that my average is 40. So the status quo, the null is always just like that it matches, it is 40. The alternative though, what we wanted to show or what we're suspecting is that it is too high. So that would be that the average is higher than 40. When you do hypothesis test, you do null and alternative. The next step would be test statistic, which for a t-test, we know t will be equal to our observed average minus expected value of our average over standard error of our average. Oh, but wait, we haven't done the preliminary work. So if you forgot, hopefully it reminds you at that step, you can say, oh, let's do our preliminary work off to the side. Preliminary work, we need our observed average. So the reason I did it like this to say, oh, maybe I forgot, is because you might not remember what do I have to do for all of the preliminary work. That won't necessarily be on your formula sheet for the exam. So because I wrote down my test statistic, I can now remember, oh, I have to find observed average, expected value average, and standard error of the average, and it kind of helps me remember everything. Our observed average is just equal to our sample average, which is 43.5. Our expected value for the average is equal to whatever our population average is if the null is true. So if the null is true, our population average was supposed to be 40. And the standard error of the average, oh wait, this is a t-test, so we have one more step to do on our t-test. I have to do SD plus for a t-test. That's the main thing to remember for your t-test. It's square root, and you have to do sample size over sample size minus 1 times the old SD. So in our case, our sample size was 4, so we'll do 4 over 4 minus 1 is 3, times an SD of 5.41, which should be 6.25. So remember, the point of SD plus was just to make that SD just a little bit bigger, because we know that our sample SD for small samples is just a little too small, so we just make it a little bit bigger. And the standard error, if you want, you can put a little plus on it to remind yourself to use that SD plus. It's just equal to SD over square root of sample size, or in our case, SD plus, since we found that. So SD plus was 6.25. Our sample size was 4, so we get 3.125. Now we've done our preliminary work. Now let's go back over here and find t. So t is going to equal our observed average of 43.5 minus our expected average of 40 over the standard error of 3.125, which gives me 1.12. Now, so we're only 1.12 standard errors away from our expected value. That's not very big. We should expect to be around 1 standard error away. So I'm guessing I might end up with a big p-value. That was my test statistic. Now let's do degrees of freedom. That's equal to sample size minus 1. Which in our case will be 4 minus 1, so 3. Then you need a p-value. For a p-value, we'll use the t-table. We draw our picture. We have t equals 1.12. Now because this is higher than, or greater than, or more than, anything like that, we will shade to the right. So for our t-table, we have a t-table. We'll use 3 degrees of freedom, and we'll look for the area in the right tail. Now you have to remember on the t-table does give us areas to the right already, so that's fortunate for our problem. We have 3 degrees of freedom, and we're looking for a t-value of 1.12, which would be about here. Which means my p-value is somewhere between 10% and 25%. I can't narrow it down anymore just using the table, so it's okay on the exam. I can just say between 10% to 25%. Let's see. So my p-value between 10% and 25%. Let's interpret that. So if I want to interpret my p-value, that means 10 to 25% of the time we will get our sample average, or one even higher, one even more extreme, if the null is true. So basically, if the null really is, if the population average really is 40, then about 10 and 25% of the time we could get a sample average of 43.5 or higher. That seems like a pretty big p-value. It is bigger than 5%. So I will say the null seems plausible. So I will fail to reject the null at the 5% significance level, because I compared it to 5%. That means it is not statistically significant. And our final conclusion, we did not find evidence that the average measurements are higher than 40. Again, I know it's kind of that double negative of we did not find evidence that they were higher than 40. We don't actually say we found evidence that they are 40, because that's not what we were looking for. We still always phrase it in terms of the alternative. So we were looking for evidence that the average was higher than 40, and we didn't find it. At least not enough to convince us. Okay, so let's double check. We figured out which test. We figured out it was one tail, and it was one sample. We did our hypotheses. We did our test statistic. We did our p-value, we interpreted it, we rejected or failed to reject, and did the conclusion. Now we have done all the work that we would normally do. Now let's turn the page and see what she asked us to do, and see if we can match it up. Okay, so B was just directions. Now you've done it, pick the right choices. So C, what are the null and alternative hypotheses for the test of significance for the situation above? So if you go back to our previous page, we said that average is 40 for the null, average is higher than that for the alternative, so it must be this one. Find the SD plus, well, we said that was 6.25. Find the standard error. Well, standard error for our average we found was 3.13. What was our test statistic? That's your t-value. Our t-value is t equals 1.12. So that one. Suppose we're told the p-value for this test equals 17%. Now on the exam, she doesn't ask you all of these steps. She'll kind of ask you some steps. So like one question, she'll say, what's the test statistic? Another question, she'll say, the p-value is this. Now what would you do for everything else? So this is common to see something where she'll tell you the p-value and then you have to do the conclusions and interpret it. So what would you conclude? Well, go back to what we said. It's always easier if you write your answer first so you don't get mixed up. We said we did not find evidence that it's higher than 40. So now, and we also said fail to reject the null. So find the thing that matches that. So it has to be fail to reject, so it can't be those. And we said there's not evidence that it's higher than 40. So not evidence, fail to reject, and must be this one. So there's not evidence to conclude that the lab's measurements are biased. Okay, so that seems to match what we had. She didn't say the average is greater than 40, but that means the same thing. If they were biased, the average would be greater than 40. And a p-value of 17% means, well, we said it would basically be a 10 to 25% chance of getting our sample average, or one more extreme, if the null was true. So let's look at this. 17% of the measurements are biased. Nope, that's not what we said. 17% chance of obtaining the sample average from the 4 measurements. That's not what we said. 17% chance that the null is wrong or that the null is right. Nope, it can only be what we write down from our definition. So 17% of the time we'll observe the sample average that we got, or one more extreme if the null is true. That matches what we wrote. And if you are told that the histogram of rates oh, oops, I will fix this before yours. The histogram of antigens is not approximately normal. Would you have been able to do this test of significance, this hypothesis test? Well, why would this matter? A t-test has a small sample size. We had a small sample size. So the central limit theorem can't kick in. So the data has to be normal. So if you were told that the data isn't normal, could you use it? Well, our answer should be no, because it's a small sample. So let's see what matches. So they said yes because of the central limit theorem. Well, that would work if we had a large sample, but the central limit theorem only works for large samples, and we have a small sample, so it can't be yes. This one says no because it's not a simple random sample. Well, simple random samples don't have anything to do with like whether or not it's normal. So she'll put this on there quite often as one of your choices. Always mark that off. If we're worried about whether or not it's normal, it's always based on whether or not it's a small or big sample. So let's go with no because it's not a large sample. So yes, we do have to have simple random samples to do our test, but what was failing here was whether or not it was normal. So we're not caring about the simple random sample at the moment, we're just caring about whether it was normal or a large sample. Okay, number 2. A study stated that the percentage of all undergraduates in Ohio felt that drinking was a problem among college students was about 60%. Sean felt it was probably higher at his university because they'd recently implemented an anti-drinking program. He took a simple random sample of 400 students at his university and found that 280 thought drinking was a problem among the college students. Conduct a hypothesis test to see if he's correct. So first of all, when you look at this, say, am I talking about percentages or averages? That will help you narrow things down. Well, I don't see anything that says averages, so this must be percentages. So we know we have percentages. Okay, then ask yourself, how many samples did you have? Well, it looks like we only had one sample. And if you want to do percentages and you only have one sample, it must be a z-test. Okay, let's see. So we need to know things like our sample percentage. They didn't actually tell us the sample percentage. They just said there were 280 out of 400. So let's do 280 divided by 400, but you have to times by 100% to make it a percentage. So 280 divided by 400 times 100 gives me 70%. And the sample size is 400. And let's see, the only other number in there that I need to worry about, or that is in there, is this 60%. So kind of our question of interest is we want to know, is the population percentage, let's see, he thinks is probably higher. So is the population percentage higher than 60%? Okay. So we figured out we want a one sample z-test for percentages. The next step then would be our null and alternative. So the null would be that the population percent is 60%. The alternative is that the population percent is higher than 60%. Again, your null has to be in equals, and then your alternative will be less than or greater than one of those two. Okay, let's see. You have your hypotheses. The next step would be your test statistic, which we know will be observed minus expected value over standard error. But you say, wait, I haven't found those yet. So you come over to the side and do your preliminary work. So we need to know our observed for our percentage. Well, that would just be equal to your sample percent, which is 70%. Then you need your expected value for your percentage. Well, that would be equal to your population percent, which if the null is true, it will be 60%. And you need the standard error for your percent. Now in your formula sheet, you'll notice this is the square root of population percent times 100% minus population percent all over sample size. So you might wonder, which percentage should you use? Well, we assume that the null is true, so we assume the population percent is 60%, so we'll use this 60% as our population percent. So that's the population percent if the null is true. So 60% times 100% minus 60% all over my sample size of 400, which equals 2.45. Make sure you don't forget to do the square root. I forgot that several times when I was making keys this week. It's an easy thing to forget, so make sure you do that. Make sure you're just always double and triple checking your work for everything you do on exams. Okay, now I've done my preliminary. My observed percent was 70%. My expected value for my percent was 60%. And my standard error for the percent was 2.45. If I put this into my calculator, I get 4.08. Now for my p-value, this is a z-test, so I will use the z-table. And this said higher than, so I'm going to shade the right tail. So this is a one-tail test. We only had one tail, the right tail that we care about. So z equals 4.08, and I want to find the area to the right. So now I open up my normal table. And I'm looking for z equals 4.08. So 4.08 would be somewhere here off the end of the table. So that means this would be close to, we're at 99.99, 99.99, so it's going to be close to about 100%. But that's the area to the right, which means if we subtract that, if this is almost 100%, then this over here would be almost 0%. So anything off the chart, you can just say almost 0. So that's your p-value. So we say there is an almost 0% chance of getting our observed sample percentage if the null is true. Okay, so in context, what we've done on our other assignments is we'd say, well, there's probably almost a 0% chance of picking something with a sample with our sample percentage of 70% if the population percent is really 60%. On exam, she kind of just boils it down to the bare bones. So it's just the chance of getting your observed sample percentage if the null is true. Now, at any significance level, that's pretty small, right? So that is a small p-value. So we reject the null hypothesis at the 5% significance level, because that's just what we always do, is that significance level. And our results are statistically significant. Anytime you have a small p-value, you can say they're statistically significant. And you say something like, we have evidence that the percentage of all students at his university that think drinking is an issue is, now look at your alternative, the population percent is higher than 60%. So higher than 60%. So higher than everyone in Ohio. Okay, now look at what she wants to ask you and see what matches. Suppose you're told the exact p-value. Now this is always using a calculator or a computer. That's how we get the exact one. Is 0.002%. What's the correct interpretation? So a 0.002 chance that the null is right. That doesn't match what I wrote. That the alternative is wrong. That doesn't match. 0.02% chance that 70% of all students say there's a problem. Okay, while you're reading these, don't think about what sounds logical. You'll mess yourself up. It doesn't matter if any of these sound logical if it's not what we wrote. So it has to be something like a 0% chance of getting our sample percentage if the null is true. Anything else has to be wrong. So like this one, 0.02% chance of obtaining our sample percentage. Close, but still not right. 0.002% of the time we'll observe the sample percentage that we got, or one more extreme. Oh, I didn't write that up above because sometimes we forget to write that part down. If the null is true. Sometimes she won't have that extreme, one more extreme. It's supposed to be in there. Sometimes we don't always emphasize it just because we really want you guys to focus on this part. So that's the part we make sure we write every time. So we can come back and add it into our interpretation. If you see her write an interpretation on the exam and she forgets the if or one more extreme, still pick it. It's still the right one. The main part is it needs to be our sample percentage or one more extreme if the null is true. Part D. The tickets in the box do not follow the normal curve. Okay, so when they say tickets in the box, it's because our book tries to tie everything back to box models. It's just a way of saying the data in the population. So the data does not look like it follows the normal curve. So could you still do this test of significance? Would it still make sense? Well, so let's go back and think about what we know about whether or not we can do things if they're normal or not. So if you have a big sample size, it doesn't matter if your data looks normal. And our sample size is 400, so it's definitely big. So we should be looking for an answer like yes, because it has a large sample size. Again, write out what you think the answer should be, then look at the choices. Otherwise, it's just too easy to get tripped up in thinking one seems logical. So let's say yes, it doesn't matter if the data is normal because it's a large sample. So that's the one we're going to go for. The third one here, we just crossed off because it said no. Okay, it says the test requires that the tickets in the box follow a normal curve. Well, that's not true. It's because our z-test says as long as you have a large sample size, it doesn't matter if the data looks normal, so it can't be that one. And 2 says yes, it doesn't matter if it's normal because it's a random sample. Well, random is good, but it doesn't affect, or I should say it doesn't compensate for not normal. So we do have to have simple random samples to do our test, but that's not what compensates for not following the normal curve. So she might have that as an answer choice, but the right answer choice has to be the one that talks about large samples, not whether or not it's random, because that's not what compensates for whether or not the data is normal. Okay, problem 3. So 20 years ago, the average time employees have been at the Postal Service was 7.5 years. A simple random sample of 100 postal employees found that the average time these employees had worked for the Postal Service was 7 years with an SA 5. So that's our current sample. A researcher believes that people now tend to change their jobs more often than in the past. So are these data evidence that the average has decreased from the old average of 7.5 years 20 years ago? So let's write down our given information. So my sample average equals 7. My SD equals 5. My sample size equals 100. And we want to know, is the average now, we want to know, has it decreased? So is it less than 7.5? That's what we're interested in asking. Okay, so let's go through and figure out what test we want to do. Do you have one sample or two samples? It looks like it is just a one sample. And how do you tell if it's going to be a Z or a T? Well, we have a big sample, which means it's going to be Z. So it's going to be one sample Z test for averages because we're talking about averages. So it's going to be averages, not percentages. Next up, find the hypotheses. The null hypothesis always has to be the one that's like equals or the same, hasn't changed. So we'll say something like the average now is the same as 7.5. It hasn't changed. The alternative would be that the average now is less than 7.5. Now test statistic, Z equals observed minus the expected value over the standard error. We haven't found those things yet, so let's find them off to the side in our preliminary work. So our observed average would just be equal to our sample average, which was 7. Our expected value for averages is always just equal to our population average, assuming the null is true, so if null is true, or whatever value you put in the null, so 7.5. And the standard error for your average is equal to the SD over square root of sample size. So my SD is 5 over the square root of 100, which gives me 0.5. So back to my test statistic now. Z equals my observed average of 7 minus the expected average of 7.5 over the standard error for the averages, which was 0.5. So this gives me negative 0.5 over 0.5, which gives me negative 1. Next step, a p-value. Well, we're doing a z-test, so we'll have to use the z-table. And because we want a less than, we will shade to the left. So that's only one tail. This is a one-tail test. We have z equals negative 1, and I want to shade to the left. So coming back to my normal table, we look up z equals negative 1. We wanted the error to the left, which luckily is what a z-table gives us. And that is 15.87%. So that's my p-value. I could interpret it. It would be something like, there is a 15.87% chance we would get our sample average of 7, or 1 more extreme, if the null is true, meaning that the sample average really is 7.5. That looks like a big p-value. Anytime you have a big p-value, you will fail to reject the null. And this is technically at the 5% significance level because I am comparing it to 5% in my head, so it's bigger than 5%, so it's a big p-value. So our results are not statistically significant. And I would say something like, we did not find evidence that, and now you write the alternative, so that the evidence that the average now is less than 7.5. So we did not find average that it was less than 7.5. So 7.5 is probably still plausible at a 5% significance level. So what test of significance would you conduct for this data? So now that we've done our work, let's see what we need to answer her things. What test of significance? Was it one-tailed or two-tailed? Was it one sample or two sample? So we set up above that it is a one sample and it is a z-test for averages. And then the only other question, is it one-tailed or two-tailed? Well, we only use the left tail, so it is one-tailed. Specifically, the left tail. But she doesn't get that detailed on the exam. She doesn't ask you if it's left tail or right tail or both tails. She just says one tail or two tail. Write the null and alternatives for this test. Well, we already did that up above, so we could probably just copy it. Oops. And this is one where she would have told you what the test statistic was, and you could have saved some time. But again, you'll do so much better if you write out all the steps. Okay, and so maybe you could have said, oh, test statistic, and so you could have skipped all the preliminary work, but still on everything else, write out everything that you have, then see what matches her choices. Okay, so the test statistic was computed to be -1. At the 1% significance level, what do you conclude? So let's see if that would be different from what we did up above. So we compared it to 5%, but in our case, we already found the p-value. The p-value is still 15.87%. The p-value doesn't change if you change your significance level, you're just comparing it to something different. So if we compare it to a 1% significance level, our p-value is still big. So we will still fail to reject, this time at the 1% significance level, because that's what we compared it to, and did not find evidence. And finally, if you were told that the data was not normally distributed, would you still been able to conduct this test? So if you have a large sample size, it doesn't matter if it's normal. We have a large sample size. So we should be good. So I would say yes, because it's a large sample. Again, simple round sample is required, but does not affect or compensate for the large sample. It does not compensate for it not being normal. So that's not going to be your answer. And this one, no, because data has to be normally distributed to use a z-table. Well, the z-table is for normally distributed things, but a large sample size with the central limit theorem guarantees that your possible averages are normally distributed, so you can use a z-table. But again, we already knew what our answer should be. It should have been something with a yes and something to do with a large sample. So we picked the second one. Number 4, the multiple risk factor intervention trial tested the effect of an intervention to reduce 3 risk factors for coronary heart disease: the serum, cholesterol, blood pressure, and smoking. The subjects were 12,866 men aged 35 to 37 at high risk for heart disease. It says 6,428 were in the intervention group and 6,438 in the control. So right away, I can tell here that we have 2 groups, intervention group and control group. So my sample size equals 6,428 for the intervention, and for the control, my sample size equals 6,438. The intervention included counseling on diet and smoking, in some cases therapy to reduce the blood pressure. Subjects were followed for a minimum of 6 years. After 6 years, they recorded the blood pressure, cholesterol, and smoking. So after the 6 years, the diastolic blood pressure of the intervention group averaged, so our sample average is 80.5 for the intervention group, and the SD is 7.9. For the control group, our statistics, now we haven't talked about this in a long time. A statistic is just something you measure about your sample data. So it's 83.6 for the average. So my average equals 83.6, and the SD equals 9.2. Did the intervention reduce blood pressure, or is our difference that we saw in our sample just due to chance error? First step will always be null and alternative hypotheses. So the null will always be that your 2 population averages are the same. So the average for the intervention and control groups are the same. The alternative would be that the average for the intervention group is what? Let's see. we wrote intervention first. We want to keep intervention first. We want to know if the intervention reduced blood pressure, so it should be smaller. So the average for the intervention group is smaller than the average for the control group. Now, looking at it, we can see that the sample average is a little bit lower, but what we're wondering, is that just based on which sample we picked, or is there a really big difference in our population averages? So was that difference just due to chance error of which sample I picked, or is there a real difference? Just like before, we know that our test statistic is going to be observed minus expected value over standard error. So I come over here to do my preliminary, and I need to find my observed average. Sorry, not my observed average. I need to find my observed difference because we're doing two samples. And I need to find the expected value for the differences. And I need to find the standard error for the differences. So the observed difference, well, to get that, you just subtract the two sample averages. So my two sample averages, I'll do 80.5. I make sure I do the intervention first because that's what I did first before, minus the sample average for your control. So mine's 83.6. So that gives me negative 3.1. Now, the expected value for your difference, if your population averages are the same, you expect your sample averages to be about the same. So the expected value for the difference should always be 0. And standard error for the difference, you have that on your cheat sheet. That's first standard error squared plus second standard error squared. At this point, I say, hey, wait, I didn't find those individual standard errors yet. So let's come back up and do it up here where we had all of our information. So standard error for your intervention is equal to, again, SD over square root of sample size. So it's going to be 7.9 over the square root of 6,428. Now that's a pretty big number to divide by, so you're going to get a really small answer out of it. So in this case, it's 0.10 if you round. And up here for your control group, standard error for an average is always just equal to SE, the standard deviation over square root of sample size. So my SD is 9.2 over the square root of 6,438. And I put that in my calculator and I get 0.11. So you'll notice sometimes it might seem like I'm kind of going out of order because it's like, oh, I could have done the SE up here a long time before. But I kind of want to show how if you're following the steps of what's written down, you know you have to find Z. Z will remind you to find the observed expected value and standard error for the differences. And that will remind you to come back into the standard error. So whether you do this first because you remember or you forget and it reminds you when you kind of go through your workflow of, oh, I haven't found that yet, and you go back to it. Either way, hopefully you'll get all the pieces that you need. Okay, so now we know our observed difference is negative 3.1. We expected a difference of 0, and the standard error for the difference was, oh, we didn't find that yet. So my first standard error is 0.10, so we'll square that, plus my second standard error, 0.11 squared, which gives me 0.15. That's my standard error for the difference. So we have negative 3.1 minus 0 divided by 0.15, which gives me negative 20.66. Now, that is a very, very, very big Z value. So I'm going to be somewhere way, way off in the tail. So negative 20.66. Because my normal table only goes to negative 4, so negative 20 is going to be somewhere way, way, way off here. That's a really, really, really small p-value. So for my p-value, I kind of skipped writing this down. We had to use our Z table, and we wanted a shade to the left because we wanted to know if it was smaller. So this is a 1 tail. We only shaded to the left. And my p-value is basically almost 0. So interpret the p-value. This would be, there is about a 0% chance, or 0% of the time, we would see such a big difference in our sample averages if the null is true, meaning that the population averages are equal. So about 0% time would you see such a big difference in your sample averages if the null was true, if the population averages were equal. Well, that is a very small p-value when compared to a 5% significance level. So we will reject the null hypothesis. Our results are statistically significant. And we found a lot of evidence, because that's going to be a really small p-value. We found a lot of evidence that the average of the intervention group is less than the average of the control group. So, was this a one-tailed or a two-tailed test? Well, in this case, we only looked at the left tail, so this is one tail. Oh, you know what we did not write on here? We didn't write which test we picked to do, did we? When we look at this, there are 2 samples. We will use a 2-sample z-test. That's the only kind of 2-sample test we learned. And it's a 2-sample z-test for averages. Let's see, find the SE difference for the averages. So sometimes that will be a question, or maybe it'll even be a completely separate question where your only step is to find the SE differences, which we found was 0.15. And what was your test statistic? Your test statistic is just your z-value. So in our case, our z-value was z equals negative 20.66. And final question. The New York Times conducted a poll on women's issues in June of 1989. One question asked, many women have better jobs and more opportunities than they did 20 years ago. Do you think women have had to give up too much in the process? Of the 1,025 women who were asked, 492 said yes. There are 472 men who were also asked the same question, and 212 of them said yes. Assume that these were simple random samples. So test if the percentage of women who said yes was higher than the percentage of men. So you might notice here, it hasn't talked about averages anywhere, but it has talked about percentages. Okay. And that fact that it's talked about percentages, and it seems like I have 2 samples. I have women and men. It tells me that this is going to be a 2-sample z-test, because we only know how to do 2-sample z-tests for percentages. With that in mind, let's write down our information. So I'm going to do women first. And I need to know my sample percentage. They didn't give me percentages, so I'll have to calculate it. So they said there were 492 out of 1,025 women. And so you divide that and then times it by 100% to make it a percentage. So I do 492 divided by 1,025 and times by 100%. Gives me 48%. And my sample size equals 1,025. And for my men, I have my sample percentage. Again, I'll do the same thing. I'll do 212 divided by 472 and times it by 100%, which gives me 44.9%. And my sample size equals 472. Now, while I'm here, because I'm doing 2 samples, I know I'm going to have to find a standard error for each sample. So you can do it now or come back later to it if you forget at this point. But my standard error for a percentage is always equal to your population percent times 100% minus your population percent, all over the sample size. I just never have quite enough room. So we'll have this. Notice this is one case where I don't know the population percent, and I don't have a null hypothesis that tells me what I think the population percent is. So I can't do the exact population percent. What I can do is I can estimate it. So I'll do these for like estimating or about, and I'll use my sample percent because that's the only thing I have. Because we're comparing two samples here, I don't have a null population percent. I'm trying to see if it is or not. So I'll just use my sample percent. So 48 times 100 minus 48, because it's the only percentage I know, so that's what I use. Divided by 1025 should give me 1.56%. And for the men, standard error for percent, we'll use that sample percentage, so 44.9 times 100 minus 44.9, all over my sample size of 472. Again, don't forget to do the square root for everything, and I should get 2.29%. So that's a lot of my preliminary work, really just writing down what they gave me and then finding the standard error. Now we can come back to our steps. We need a null hypothesis. So the null would be that the percentage of men, sorry, we did women first, women who said yes is the same as the percentage of men who said yes. The alternative is they think there are probably more women who said yes. So the percentage of women who said yes is higher than the percentage of men who said yes. Next step is your test statistic. Z is supposed to be equal to your observed. Now we're talking about differences, so I could write difference minus the expected value of your difference over standard error of your differences. But I haven't found any of those, so let's find them over here in our preliminary work. You need an observed difference. Well, that's just what is the difference in your sample percentages. So make sure you do women first because we wrote women first. So our women percentage is 48% minus our men percentage of 44.9%. Which gives me 3.1%. The expected value for your differences. Well, if the null is true, we assume that our population averages are the same. So our sample averages should be about the same. So the difference should be about 0. And the standard error for your differences, well, that formula is on your sheet. It just says take the first standard error and square it and add the second standard error and square it. So square root, oh, and don't forget the square root. So it'll be 1.56 squared plus 2.29 squared, which should equal 1.12. Nope, sorry, that's the wrong calculation. Should be 2.77%. That's our guess for the standard error for the difference. So our observed difference is 3.1% minus our expected value of 0% over our standard error of 2.77%. Which gives me 1.12 as a test statistic. Well, remember, a test statistic is just telling you, or a z-value just tells you that that is 1.12 standard errors from your expected value. And we always expect to be about 1 or 2 centimeters off, so that's probably not too surprising. That's probably possible. I would probably guess this is going to be a big p-value. But let's find it to be sure. So the p-value, this is a z-test, we will use the z-table. And we're looking for higher than, so we will shade to the right. Z equals 1.12. Shade to the right, come to the normal table. We're looking for 1.12. So the closest I'll get here is probably about 86.43. Oh, but wait, that's the area to the left. So if this is 86.43%, then this has to be 100% minus 86.43%. So 100 minus 86.43 gives me 13.57%. So my p-value equals 13.57%. Now that's off just a little bit because I had to use the table, so her answer might be just slightly off. Pick whatever it is. So like if she used the calculator, she would have got 13.3. So we got 13.57. The calculator would say 13.3. So just kind of pick the closest one there. So our interpretation of our p-value will once again be something like 13.5% of the time, because we can say that or a 13.5% chance. 13.5% of the time we will get such a big difference in our sample percentages if the null is true. And that means if the null is true and there is, and let's see, and the population percentages are the same for the men and women. So again, if those population percentages are the same, then about 13.5% of the time we would get such a big difference in our sample percentages. That's always talking about if you took lots and lots of different samples, you get different sample percentages. So 13.5% of all the different samples we could have picked would have given us such a big difference in the sample percentages. Well, that's pretty big. The null seems plausible. That is a big p-value. It is bigger than 5%. That's what I'm comparing it to. So I will fail to reject the null. And I would say we did not find evidence that the percentage of women is higher than the percentage of men. So coming down to the end, just to make sure, she might ask you things like, which test did you use? So you would say it is a 2-sample z-test for percentages. She might ask you, is it one-tailed or two-tailed? So it is one tail. Specifically, this one was a right tail. Sorry, we didn't have any two-tailed tests on this specific review, but there are some on the extra credit review. And was it 1 sample or 2 sample? Well, obviously we just said it is a 2-sample.